Yeah, thanks for the introduction. Can everyone hear me fine?
Yeah, okay.
Good there? Yeah. So yeah, what I would like to show you today is an overview of some of the results we've obtained in the framework of a project to look at the influence of climate change on the frequency and magnitude of glacial lake outburst floods in Patagonia. So that's of course not work that I've been doing alone. Most of what I will show today are actually data to obtained by two PhD students in the group, listed here at the bottom, Elke van der Kerkhove and Dawei Liu, and also the postdoc of Benjamin Amin. So yeah, for those of you who don't know me, I'm Sebastian. I'm based at Paris-Saclay University in France now, but it's rather recent. Until a bit less than 2 years ago, I was at Ghent University in Belgium, where most of the work that we'll present today has been done. So I would define myself as a sedimentologist and sedimentary geochemist, and I mostly work with lake and fjord sediments. And what I do with those lake and fjord sediments is to reconstruct first hydroclimate. And what I mean by hydroclimate is mostly variations in precipitation and in river discharge. I also use especially fjord sediments to reconstruct the evolution of glaciers during the Holocene. And then more recently, I started to look at those sediment records to look at natural hazards that are linked to those changes in precipitation and in the evolution of glaciers. And we do that using all types of sediment cores, from very short sediment cores that we take ourselves in proglacial lakes, like this one here with a short UVTech gravity coring system that many of you, I guess, have used, to slightly longer sediment cores that we take ourselves from this small research vessel here that was built for the fjords in Patagonia, to much longer sediment cores, like the ones taken with the Palmer icebreaker or with the French Marion Lefren research vessel here. And I've mostly been working in Patagonia, in this, at the southern tip of South America. And the original reason for that is that we wanted to reconstruct the evolution of the southern westerlies. So I guess some of you know about the southern westerlies. They travel across the Pacific Ocean here, and they bring a lot of moisture towards the Andes here in Patagonia. And Patagonia is actually well located to reconstruct the evolution of the westerlies because it's the only continuous landmass that intersects the entire western wind belt that you can see here in green. And so what I have done and what many others have done in Patagonia is generate precipitation records from the western side of the Andes. So that's the wet region here where precipitation is almost entirely driven by those westerlies. So we have generated paleoprecipitation records along a transect from north to south to reconstruct the evolution of the westerlies during the Holocene. Then I started to work a bit more on fjord sediments, not only to look at precipitation, but also to look at glacier variations, and mostly glacier variations during the Holocene. So what you see on this map here in blue is the extent of the Patagonian ice sheet during the glacial maximum, covering most of the southern Andes. And in white, we have the two ice fields that are left, the leftovers from the larger ice sheet that was covering the region during the LGM. So we have been using sediment cores from those fjords here to reconstruct the evolution of the glaciers in Patagonia. And then, as I was saying, more recently, we started to look at sediment records to reconstruct natural hazards, mostly floods, linked to those variations in precipitation and in glaciers. That's, of course, what I will be talking about today. So yes, what I would like to show you today is our results that we obtained to look at the influence of climate change on the frequency and magnitude of glacial lake outburst floods. So I guess not everyone in the audience is familiar with glacial lake outburst floods. So these glacial lake outburst floods are basically floods that originate from a glacial lake that is dammed by either a moraine or a glacier. And this is an animation here that will show you an example of one of these glacial lake outburst floods. So here we have a glacial lake high in the mountains, receiving meltwater from the glaciers. The lake level rises. In this case, the lake is dammed by a moraine. At some point, the moraine breaks, and all of the lake water creates a flood in all the downstream environments. So the example of the moraine is one type of glacial lake outburst floods, but there are many glacial lake outburst floods that actually occur when the ice dam breaks and triggers the inundation of all the downstream region. The main difference is that if we have a lake dammed by a moraine that creates a gulf, it will only happen once. If we have a lake that's dammed by a glacier that creates a gulf, the glacier can regrow and we can have several gulfs from the same lake through time. It has been observed that in some region we actually have 2 or 3 of these gulfs per year when the lake regrows and allows the lake to refill. And of course, as most floods, that creates the inundation of all the downstream environments, affecting the populations that live there, the animals, the cattle. So there are large consequences for everything that is downstream of those lakes. And yeah, we can have glacial lake outburst floods basically everywhere on Earth where we have glacial lakes. So this map here shows the presence of glacial lakes on Earth. There are lots of them in Alaska, northeastern Canada, all around Greenland. In the Andes, it's mostly here, Peru, and a bit Bolivia, and of course here, Patagonia. And then there's Norway, there's lots in the Himalayas here, and some of them in New Zealand. And if we look at the evolution of all these glacial lakes during the last recent decades, this is what we see here. So the volume and the size of glacial lakes has been measured during the last 30 years. And if we look at global numbers, the number and the volume of those lakes has increased by about 50% during the last 3 decades, so during the last 30 years. And that's basically what you see on these 4 maps here. So the colors show the change in the volume of those glacial lakes. So the warmer colors show that those lakes have been growing. And if you compare a bit these 4 different maps here, you directly see that the darkest red colors are here in Patagonia. And if you look at numbers for Patagonia, you can actually see that those glacial lakes have more than doubled in volume during the last 30 years. So that increase in the size and in the number of those glacial lakes is something that's pretty well known because it can be observed directly from satellite data. What we don't really know is how this has affected the frequency, the magnitude of the glacial lake outburst floods that originate from those glacial lakes, and that's what we wanted to look at. Actually, my main interest in glacial lake outburst floods started with this note that was published in Nature more than 15 years ago. Now I was just starting my postdoc in Woods Hole, and in that note, they basically describe park rangers in a park in Patagonia doing their regular hike in the park and had seen the lake as they were used to see it. They went back to the same location the next morning and the lake was gone. That's kind of what we see on the image here. The lake bed is here and the entire lake is gone. And so they had observed basically a lake that disappeared overnight and that confused geologists. Now we know, of course, that this was just one of those glacial lake outburst floods, but that's what triggered our interest in glacial lake outburst floods in the region. So if we look at Patagonia, so we are here at the southern tip of South America. This is the northern Patagonian ice field. There's a second one a bit larger for the south here. But most of the glacial lake outburst floods during the last few decades in Patagonia have occurred on the eastern side of this northern Patagonian ice field. And most of them originate from this small lake here called Lake Cachet-d'Os, which is dammed by the Colonia Glacier. If we look at that lake and at that glacier in more detail, this is what we see. So this is the lake here. It's about 3 kilometers long. It's dammed by the Colonia Glacier here. And every now and then, when there is a gulf, the water of that lake goes either under the glacier or on the side of the glacier here, enters Lago Colonia, and then continues downstream to Rio Colonia, and then to a larger river that's called the Baker River. And what you see on the left here is the lake after a gulf. So you can just see that's where the lake used to be. There are just a few icebergs left at the bottom. The lake is gone. And this is the Colonia Glacier that blocks that lake when there is water in that lake. Here again, you can see an image of the lake before a gulf when it's full of water, and here right after a gulf when it's empty with just a few icebergs at the bottom. So it's a huge amount of water that is discharged within a few hours. And if we look at hydrographs from downstream stations, this is a station on the main Baker River, a few tens of kilometers downstream. This is what we see in black here. So that is the largest river of Chile in terms of discharge. So the regular discharge is close to 1,000 cubic meters per second. But then when there is a gulf, you can actually see that the discharge increases up to 3,000 or 4,000 cubic meters per second. The increase is pretty abrupt. It just lasts a few hours. Then you can see very high discharge conditions for about 1 day, maximum 48 hours. And then we go back to regular discharge conditions. Same thing here, another gulf that occurred in a different seasons. The background value is a bit lower, but the increase is pretty similar, around 3,000 cubic meter per second. And of course, since we inject meltwater in the main river, temperature here in red drops, which is pretty typical for these glacial lake outburst floods. And that's what you see if you go along the river right after one of those gulfs. So that's a clear sign that the water level was pretty high and was able to transport these pretty large icebergs. If you look at the size of the trees here, those trees are 3 to 4 meter high. So these are pretty large icebergs transported by the gulf. And further downstream in the floodplain, this is what we observe. So it's not the exact same valley; it's a valley next to it. That's the Huemules River Valley coming down from another glacier here, also linked to the northern Patagonian ice field. But in regular times, the Troglacial River here is just a 10 to 20 meters wide river that is limited to the western side here of the valley. What you see here during a gulf, the entire valley gets flooded. And to give you an idea of the scale here, that valley is about between 1 and 1.5 kilometers regions that get flooded when those gulf occur. That lasts for about 2 days, and then it's over. We go back to regular conditions. So yeah, from the historical data and from the river discharge data, we know that there's been 23 gulfs in that region between 2008 and 2020. We also know that before that, between 1968 and 2008, there were no gulfs at all. And so the goal of our project here was to generate late Holocene sediment records of gulf frequency and magnitude to try to extend that historical record further back in time. The limit here at 1968 is just when the first monitoring stations have been installed in those rivers. So there is no discharge data before 1968. Now, if we go back to the map that I showed a few minutes ago, you remember that most of the gulfs originate from this lake here, down by the Colonia Glacier. And then when there is a gulf, water from that lake enters into the Colonia River here, which merges with the larger Baker River and then flows downstream towards fjord here. And so my first idea when we started that project was, of course, to go into that fjord and get sediment cores. Now, using sediments has flood archives is not anything new. That's been done a lot by the lake community. And in the lake, things are pretty simple. When there is a river, when there's a flood entering a lake, the density of the river water, which is loaded with sediment, is much higher than the density of the lake water itself. So that flood sinks directly at the bottom of the lake, creates a turbidity current. And so those floods are recorded as turbidites that are easily visible in the sediment. Now that works well in lakes because lakes are composed of fresh water. In fjords, things are a bit different. Things are a bit more complicated because the fjords are highly stratified. There's a strong salinity gradient in fjords. The bottom water in general is almost seawater, but the surface water is either fresh water or sort of brackish water. So this is, for example, a profile of turbidity here, showing where the sediment is located in that water column. The water or the river water input is here on the left side of the graph, and you can see that most of the sediment is transported in the upper part of the water column, in the upper 5 to 10 meters. The water there is brackish, and most of the sediment is located here in the upper part of the water column. That means that when we have a proglacial river entering a fjord, most of the sediment is concentrated in the upper few meters of the water column and does not easily create bottom currents, does not easily sink at the bottom as it does in lakes. So in theory, to create bottom currents, to create turbidity currents in fjords, we would need suspended concentrations that are much higher than 1 gram per liter to basically overcome density contrast and allow that river water to sink at the bottom of fjords. So the first thing that we did in that region was to do a multi-beam map to try to understand if those GLOFs, those glacial lake outburst floods, actually created turbidity currents or not in the fjord. Now that's a region that's pretty remote. The chance we had is that there is a small research vessel that you see here that was built by the University of Concepcion in Chile for research in those fjords. Of course, it had no multi-beam system, so we had to bring all our equipment. And given the distance, it was quite a bit of an adventure. We had to ship half a ton of equipment, take it down a gravel road to close where this town is located. And of course, the town is not directly connected to the road. So we had to take all that equipment that you see here in these aluminum boxes on small boats through the river to reach the town where the University of Concepcion has a small coastal research station. So we spent quite a bit of time bringing the equipment there. And then we had to, of course, install it on the boat. So the captain spent a few days building a structure to be able to install that multi-beam echo sounder at the bow of the ship. This is what we installed the electronics inside of the boat. And after about a week, we finally had that equipment, the multi-beam echo sounder here installed in front of the boat. You have the two transducers here. That's a structure that can be lifted when we do not make measurements, but then we bring it down in the water when we start measuring. And then what you see on top here is a motion sensor that corrects for the movements of the boat during data acquisition. So we then spent about 2 weeks going back and forth in that fjord to create that multi-beam map here. So that's the map right in front of the river mouth. So that's the river where all the GLOFs come from. we can see a large delta here that goes from about 0 meters here to 300 meters at the bottom, and a flat area here. But if you look into more details at that map, what you see is that there is a submarine channel cutting through the sediments here. So here, there's that submarine channel, which means that at some point we have turbidity currents that sink at the bottom of the fjord and transport sediment to the deeper environments. We still don't know if those turbidity currents were related to bluffs or to other types of floods, but at least it meant that we had to pay attention to the different locations in the fjord to take sediment course. Now, the next step to understand a bit better how these bluffs were recorded in the sediment was to deploy a sediment trap. So we installed a mooring at a depth of about 200 meters in that fjord, with several pieces of equipment, of course, on the mooring. But the two main pieces of equipment on that mooring is this. That's a turbidity logger that measures a turbidity every hour in the upper part of the water column. So we installed that turbidity logger at 2 meters below the water surface. So it measures the amount of suspended sediment in that fresh or brackish water lens that transports most of that sediment. And then below that, close to the bottom of the fjord, we installed a sequential sediment trap. That's a sediment trap. So inside of this is a large funnel, and it has 24 bottles at the bottom. And these bottles turn every 2 weeks, which means that we have 2 weeks of sedimentation per bottle, but we can leave the sediment trap for 1 year in the fjord, and after 1 year, we get a full year of sedimentation divided in 24 bottles. And those are some of the data that we obtained on that sediment trap. On top, the blue curve is the daily discharge of the river. So as I was mentioning earlier, it's close to 1,000 cubic meter per second. Of course, higher in summer when there is a higher meltwater input. Here we have the suspended sediment concentration measured with the turbidity logger on the mooring. And if you compare the two curves, they seem pretty similar. The amount of sediment that we see suspended in the fjord basically reflects the amount of sediment that's supplied by the river. And then if we look at the bottles in the sediment trap, that's what we see here at the bottom. You can see basically the same pattern here. Lots of sediment being supplied here in summer and very little sediment here in winter. Unfortunately for us, there was no bluff that occurred between those 2 years, 2017 and 2018. So that didn't really help to identify the nature of the bluff deposits in those sediments, but at least it allowed us to understand that most of the sediment in that fjord was deposited in summer, and also that we had pretty high accumulation rates, close to 3 centimeters per year. We then moved on to the next step and started to collect sediment cores on both sides of the channel, here in the north, here in the south, as well as in front of the deep water mouth of that channel here, to start looking at the bluff deposits in those sediment cores. So what I will show you now are mostly data from this sediment core here, the 08. This is that sediment core here with a regular lithological column here on the left. Here we have grain size data showing pretty fine grain sediment. That's TOC, also pretty low values between 0.2 and 0.5 more or less. And here is the H model that's based on Lat210. And the first thing that we see when we look at that sediment is that in the upper 30 centimeters, more or less, there are several layers that we highlighted here in blue, with finer grain size, close to 4 microns, very low TOC, about 0.2%, and those layers are all pretty recent. If we look at the age of those layers, the first one here started here in 2008. And if you remember what I mentioned earlier, about the historical data on those glacial lake outburst floods. The first one started in 2008. So that's clear evidence that all those blue layers here represent the recent glacial lake outburst floods from that lake captured DOS. So that means that glacial lake outburst floods in that fjord are recorded as fine-grained sediments and organic pore layers. And that was a bit counterintuitive at the beginning because as cementologists, we always expect to have the high energy deposits to have floods recorded as coarser particles. But then when you think of it, it makes sense because all the sediment that is reworked during those glacial lake outburst floods is pure glacial sediment. It's very fine-grained. It's the typical glacier rock flour, which is 3-4 microns in size. There's almost no TOC. And so in this case, the flood deposits are actually finer grained than the background sediment, and they have a lower TOC just because they represent glacial sediment. Now, if we look further down in that sediment core, we can see two other of those event deposits here. There's the blue one, fine-grained, low TOC, and the slightly coarser one here is more turbidite with higher TOC values. And those two layers were not related to known historical graphs. So we looked at that in more details and then started doing some provenance measurements on those deposits. And provenance in the region works pretty well because the lithologies on both sides of the Baker River here is very different. On the western side, where all the glaciers are located, where the bluffs come from, the lithologies here is mostly granite. If we look at the other side of the river, where there are almost no glaciers, the lithology is dominated by metamorphic rocks. So if we basically use any isotopes, here I just represent neodymium, but we did the same using strontium, we could do the same using lead and other isotopes. We can basically use these isotopes to easily track the provenance of the sediment. And that's what we did here. So you can directly see that the glove layers, of course, originate from the green lithology, so from the region where the glaciers are located. Same thing for the background sediment. Those glaciers are the main suppliers of sediment to that fjord. Here we see that this turbidite here has a different provenance. So that one has sediments coming from the eastern part of the watershed. And that's a deposit that we could relate to an historical rain on snow deposit. So that's the second main source of floods in the region. When there is snow on the ground, when it rains on that snow, the rain melts the snow. It basically creates double the amount of water and can create pretty large floods. So that's a rain and snow event that mostly affected the eastern side of the watershed because it occurred in winter. Then in winter, everything here on the west is frozen. And then below that, we also had another rain on snow event. That one mostly affected the western side of the watershed because it occurred in summer. In summer, there's no snow here on the ground, but there is snow here, and when it rains on the snow here, that creates one of those rain on snow flood deposits, which have the same signature as the globs because it comes from the glacier area in that part of the watershed. So those are two rain and snow events. So the bottom line here, the main message, is that the glacial lake outburst flood deposits are recorded as very fine-grained sediment, finer grained than the background, with very low TOC. So that's just one sediment core, and we see that one of the main proxies to identify these glacial lake outburst floods is grain size. So the finer grain size here is a clear indicator. Now, measuring grain size on sediment cores is, of course, a bit time-consuming, especially if you want to do it at high resolution. Here it was done every 5 millimeters. So what we did to be able to apply that to other sediment cores was to come up with a technique to actually predict sediment grain size from inorganic geochemical data. We basically use X-ray core scanner data, select the elements that mostly reflect grain size, and based on that, predict sediment grain size. So this is the sediment grain size here for the same sediment core that is predicted from the XREF data. And we see the exact same pattern, very low values here in the Glacial Lake Outburst Flood deposits. We actually went a step further and used the rest of the XREF core scanner data to interpret the provenance of the sediment and then build a k-means clustering technique that is able, based on grain size and on provenance, to identify the flood layers and classify them into Glacial Lake Outburst floods here in blue, based on their fine grain size, and rain and snow events like this big one here in orange. So that column here that you have on the right is only based on the k-means clustering analysis of XREF core scanner data, of course trained with real measurements we had on that sediment core. But the main advantage here is that once we understand what drives the geochemical position of that sediment, we can apply the same technique to all sorts of sediment cores coming from that basin without measuring grain size, without remeasuring other variables. That's what we did here. We applied that all sediment cores from the same basin, and you can see that in blue here that all of the Glacial Lake Outburst flood deposits are in the upper part of the sediment cores. The signal is pretty homogeneous across that part of the basin. So we have a very good proxy to identify the Glacial Lake Outburst flood deposits. The main issue remains that we have very high accumulation rates, and so the oldest core that Ray got here is only reaches 1970. So for what we wanted to do, go further back in time, that was a strong limitation. So to solve that issue, we actually worked on a different type of sediment archive, and that's what I will show you during the last part of the presentation. If you remember, again, the origin of those Glacial Lake Outburst floods, the lake is here, it's dammed by the Colonia Glacier, and during the Gloughs, the water enters the Colonia River here, and it reaches the larger Baker River that flows from north to south. And if you look at what happens at the confluence here during Glacial Lake Outburst floods, the amount of water that discharged by the Colonia River here is so high that it blocks the regular flow of the Baker River. And that creates the inundation of upstream environments, so floodplains located in that region. That's what we see on this image here. The large river, the Baker River, goes from the top here towards the right. The river here, Colonia River, is the one that receives the Glough. And then when those gloughs occur, the amount of water in that river is so important that it blocks the flow of that river, and it starts triggering the inundation of all the upstream environments. And that's what you see here, the floodplains that are flooded here right after one of those gloughs. Those are two images that show a similar situation during Glough. Here, the Baker River goes from left to right. You can see the glacial sediment coming in during a Glough. And you can actually see the sediment that starts flowing upstream. Same thing here, the Colonia River is here. During a Glough, you see the sediment plume here that goes up the main river, Baker River, and reaches all the upstream floodplains. So of course we went to those floodplains, and when we started working on those floodplains, I decided to collaborate with an historian, and his job during field work was to go interview all the settlers in the region. So people who arrived there in the 1940s when they were kids. So they are pretty old now, and they love telling stories. And the main story that we heard from most of them is that when they were a kid in that region, they had observed those Glacial Lake Outburst floods in the 40s and the 50s. There was in general one every summer. And the way they describe those floods is that after the water receded, they were always finding sheep left, that of course on top of the trees. So that gives us an idea of the size of those gloughs. So the water level was rising by 5 to 6 meters. So we went to that floodplain, collected several sediment cores. These are 3 of the PhD students who worked on that project. We collected those sediment cores on both sides of the river. These are the yellow dots that you can see here. And those sediment cores were between 2 and 5 meters long, and they all covered about 3,000 years. So finally, we could get records much longer than what we had from the fjord sediments. One important point about all these sites here is that we only selected sites in the floodplain that were located about 5 meters above the present-day level of the Baker River. This means that only the high magnitude floods can be recorded at those sites, and we will not register every single little flood that might occur every now and then. So we went to those 4 sites, obtained sediment cores, and my main idea by going there was that we would find basically peat bogs and a few glacial mud layers in those peat bogs. What we found was sort of the opposite, lots of glacial sediment. That's a typical, again, fine-grained glacial sediment. And in that glacial sediment, there were periods where we had lots of peat, or at least organic-rich deposits that represent periods of quiescence, so periods in which we had no glove for probably several decades. And here, all of that is sediments coming from the gloves. So what Elke did as part of her PhD is that she analyzed those 4 sediment cores. She actually did a bunch of LOI measurements, loss and ignition. She loved it. She measured LOI every 5 millimeters on those 4 sediment cores. And then we combine all those data sets to come up with that composite record here. So this is the same composite record showing data over the last 3,000 years. Here I plotted the inorganic content of the sediment towards the top. So a lot of inorganic sediment means lots of these high magnitude glacial floods. If the inorganic content decreases, it means that we have more peat, so periods of quiescence with no or very little glacial lake outburst floods. And if we look at that record, what we directly see is 2 main periods with high magnitude glacial lake outburst floods. There's one here, which is between 700 years ago, more or less, and roughly 100 years ago. And then another one here between 2.5 and 2.2 kiloyears BP. So those are 2 periods with lots of high magnitude glacial lake outburst floods. But in between, we had pretty organic rich sediment, so way less floods. If we now compare that to the evolution of the glaciers in the region, this is what we see. So there are several neoglacial advances that have been described in Patagonia. There's number 5 here, which is basically the equivalent of the Little Ice Age in the Northern Hemisphere. And what we see is that there are lots of floods during the neoglacial advance number 5. Same thing here, lots of flood during neoglacial advance number 3. Also plotted number 4 on this figure here, but that's one that has only been described for the southern ice field that does not affect this region, so we can basically neglect it here. So the main message by comparing the floods here to the glacier variations is that those high magnitude glacial lake outburst floods that we registered in the floodplain sediments mostly occur during periods of neoglacial advances when glaciers are larger. Now that also seems a bit counterintuitive, but we have an explanation for that. So I have 2 cartoons here that will show you how that works. So think of a neoglacial maximum, think of the Little Ice Age, for example. Glaciers are larger and thicker. So that's what we have here, large glaciers, highest volume is high. If we have large and thick glaciers, those glaciers are able, they form strong dams, and those strong dams are able to retain huge amounts of water. That's what we see here, large glacial lakes. Now, we have large glacial lakes, but we also have very strong ice dams. So those ice dams do not break very easily. So the frequency of those bluffs is pretty low, but when they break, they release a large amount of water. So the bluffs that occur during the glacial maximum are high in magnitude, and that's what we register in the floodplain sediment. If we look at the neoglacial minimum, similar to the present day situation, glaciers are smaller, the ice volume is low. Smaller glaciers, thinner glaciers cannot hold as much water in the glacial lakes that dammed by those glaciers. Here's a small proglacial lake here. So the glacial lake volume is low. The ice dam is pretty weak. Glaciers are small, so those ice dams can easily break. So the Gluff frequency is high. But then the magnitude of those Gluffs is pretty low because the lakes are pretty small in size. So that's what we see in the present day situation. We have lots of those glacial lake outburst floods, but compared to the past, their magnitude is pretty low. So the main message here is that the high magnitude glacial lake outburst floods are more frequent when glaciers are larger and thicker here, mostly because they can retain larger glacial lakes. So to conclude, I just have a few take-home messages. The first one in terms of Gluff archives is that fjord sediments actually a very good high-resolution Gluff archive. We can easily identify the Gluff layers, low grain size, low TOC, but the issue here is that we have very high accumulation rates, which is great to obtain high-resolution records, but we cannot go much back in time because we would need sediment cores that are 7/10 of meter long, which is almost not feasible in those fjords. So we had to turn to floodplain sediments, and those sediments covered the last 3,000 years. Now, in terms of glacial lake outburst floods, the first observation here is that Bluffs in Patagonia are not new. They have occurred during the entire late Holocene. What has changed through time is the frequency. So the high magnitude glacial lake outburst floods, what you see here, the frequency is high now, but the magnitude was much higher in the past when glaciers were larger and thicker. So the Bluffs that we see now, yes, they exist, they are frequent, but they're not as high in magnitude as they were in the past. So in terms of present-day climate change, it means that the present-day climate change results in an increase in the frequency of Bluff, but a decrease in their magnitude. And that is in line with a very recent data has been obtained from satellite observations trying to track the frequency, the magnitude of those Bluffs linked to those changes in the glacial lakes. Thanks.
Thank you very much. That was really, really cool. Really interesting. So thanks a lot. We'll turn now to opportunities for questions. And as usual, we'll start off with the group in Bergen. If you have any questions, Jostein and the gang. Hang on, I need to unmute. Sorry.
Hello, yeah. We have a question about a bit about what you summarized with. So you summarize with now we see a increased frequency and a lower magnitude, but do you think that will change in the future, or is that the trend?
Yeah, the increase in frequency that we have observed in the last few decades is, of course, there because we have lots of glacial lakes now. But to have glacial lakes, we need glaciers. Of course, at some point in the future, glaciers will continue to shrink, will continue to disappear. So at some point, the amount of glacial lakes will also decrease. So if the number of glacial lake decreases, then we will reach a point where the frequency of those bluffs also starts decreasing, or at least they will move somewhere else at higher elevations and higher latitudes.
Thank you.
Any other questions from the group? Yeah. Second.
Yes, I have a question. So you use loss and ignition, 4 different records to show floods, and then you combine all of them later on. Can you explain how you combine those records?
Yeah, so we obtained independent edge models for each sediment core. So for each sediment core, we obtained a series of C14 edges, which was pretty easy because we have lots of peat organic rich deposits all along those sediment cores. So I had someone pick some macrofossils of always the same plant species to the C14 on that. Then for each sediment core, we created an edge model and we plotted LOI versus the age of that same sediment core. And then we put all of those sediment cores together, basically sum up all the LOI values versus age, and created the average of those 4 records.
Okay, thank you.
Does that make sense?
Yeah.
Okay. Any other questions from Bertrand? No. Okay. What about here in UMass? Questions? Yes.
What was one of the key, or when you used XRF to estimate grain size, what were the key elements in the XRF scan that linked to grain size?
Yeah, very good point. That's something that I only showed one slide on that, but we have actually several papers on that. What the technique does is that it gives a different weight to each element. And the elements that contributed the most to the prediction are all the classic lithogenic elements. That's zirconium, that's titanium, that's rubidium for the fine sediment, potassium for the fine one too. And the reason we wanted to combine several of those elements is instead of just using one or one elemental ratio, as lots of people do, is that we have actually shown based on river sediments that there's not a single element or a single elemental ratio that reflects grain size along an entire range. If you look at the relation between chemistry and a range of grain size values, those relations will drop at some point. So by combining different elements, we were able to reproduce the real grain size much better than just by using one or two elements. But yeah, in total, there are 7 or 8 elements. We fine-tune a bit the element that we use depending on the environment. If we are, for example, in the open ocean where there is lots of carbonate productivity, we'll of course not use calcium. Same thing if we are in the lake with biogenic silica, we'll not use silicium. But we put all the lithogenic elements into the model, and then the model gives a different weight to each element. Yeah. Does that answer your question?
Yes, thank you.
I have a small one.
Yeah. Another question from here.
You mentioned, I'm not sure of the year 2006, I think. There's a rainfall on snow in the eastern. Yeah. Do you have any observational data, like meteorological data, that supports this? Or?
Yeah, there is. That's why we could actually link that to a rain and snow event. That's not just pure interpretation, but all those short sediment cores are 1 meter long. They all have historical data from weather stations and from river discharge. And so by comparing river discharge to weather station data, precipitation and temperature for the snow on the ground, we can actually make the link between those deposits and real conditions in the watershed.
Okay, thank you. Another question? Yeah.
I have a question if there's time.
Hang on a minute, Julie, go ahead.
Okay.
Yeah, you said that you sampled grain size every 5 centimeters. How did that compare in the deeper like lake sediments versus the floodplain sediment? Did you use the same sort of did you need a lot higher resolution in the floodplain sediment to deduce the grain size?
Yeah, in the floodplain, we didn't use grain size much. We mostly used LOI. We just did a few grain size measurement to confirm that the gray inorganic sediment that we were seeing was actually glacial mud and not something else. But in the floodplain sediments, we cannot see individual bluff layers. Resolution is way too low, and then if we have several bluffs that occur within a few years from each other, there's not enough time for vegetation to regrow and mark the difference between those layers. So that's why I put on my take-home message slide here that the best bluff records actually the fjord sediments, because if we do grain size at high resolution or predicted, we can identify almost every individual bluff layer. In the floodplain deposits, we can't. We just see periods with more or less floods, but we cannot identify those layers individually.
And then in regards to the carbon-14 samples you pulled, did you pull the same amount from the floodplain sediment cores as the fjord sediment cores, or did you focus again more on the fjord sediments because of that IQ?
We only did C14 on the floodplain sediments. The fjord sediment cores are way too young, and there is almost no carbon and no macro remains in those proglacial deposits in the fjord. So the age model in the fjord is based on lead-210, and in some other cores, cesium-137, but there is no C14 in those fjord sediment cores.
Great, thank you.
Thank you. Julie BG.
Yeah. Hi, Sebastian. Great talk. I was just wondering, have you had an opportunity, given that you had some historical connections with the local people, to talk about your findings with all the people in the catchment to influence land use or, flooding that may affect their infrastructure? Have you talked to the indigenous people?
Yeah, we do. Actually collaborate quite a bit with the local branch of the government that is in charge of water management in general. And so in the last few years, they started installing more and more monitoring station in those rivers. They started installing an early alert system. So when they put water level sensors in those lakes that send messages through VHF radios to the people living in those watersheds. And then what I'm trying to increasingly do is that every time I go there for field work, I give a small presentation to those local communities in the village where we use that boat, and I'm starting to do radio interviews there to try to communicate a bit more to the local populations about those risks. But the branch of the government, the regional branch of the government that takes care of that, is very active, and they are taking all those results into account to inform the populations too.
Yeah, fantastic. Thank you.
That's great. I have a quick question too. When you showed the map of the watershed that drained into the field, there were a lot of other rivers and in some cases lakes and glaciers that may have also had cloths. How do you sort of separate out the signal from the specific site that you were working on?
Yeah, we can't really tell from which lake those gloves were. Actually, we know that. So the Cachet DOS here is the one that triggered gloves during the last 20 years. But before that, the gloves that the first settlers were talking about were actually from a different lake that was located in that valley here. It's a bit hard to see. So there used to be a lake here, and the gloves in the 40s and 50s originated from this lake here. And so just depending on the configuration of the valley and the exact size of those glaciers, the source lakes will change through time. And it was one of the reasons that I wanted to look at those fjord sediments, is that by going there at the outflow of the main river, we basically incorporate all bluffs coming from all over the eastern side of the ice field. So to me, those fjord sediments is still the best archive if we at some point manage to get long sediment cores, because they do not depend on the shape, the morphology of one single valley, one single glacier, but they really get a record that is representative of the entire eastern part of the ice field. Does that answer your comment?
Yeah, I was thinking about those little glaciers on the bottom right-hand side as well.
Oh, those here.
Yeah, nothing.
Yeah. Yeah, those are pretty small. There's almost no glacial lake there. There is one small lake that's not even on the maps somewhere here, and there are like that 3 cabins along the valley here, and people there have described one small glacial lake outburst flood. We looked for it on in the sediment cores in the fjord. We do not see it. We tried to use floodplain sediments from all that region here. We can't really see it because it's a pretty small in volume bluff. So when it enters a river that has a discharge of 1,000 cubic meter per second, it increases 20, maybe 50 cubic meter per second, but that's it. So it does not really change the amount of sediment that reaches the fjord. So yeah, it's possible that we've had small bluffs from here that we do not see, but historically, there's only one that we know of.
Okay, thank you. Any other questions from the assembled listeners?
I've got one more.
One more. Okay.
This is all a seismically active area, presumably. And do you see any correlation between the history of earthquakes in the region and presence of bluffs?
Actually, it's not seismically active. The central part of Chile is, of course. There's no question about it.
But not that far
south of 43, 44 degrees south, it is very quiet.
Okay.
We've looked at all the seismographs in that region. There's nothing. We've looked at it in details because there are lots of sediment records in that region too, and there's not a single earthquake-triggered turbidite. So there's the seismic activity is pretty low.
Okay.
There are volcanoes though.
Yeah. Okay. All right. Well, with that, we'll stop, and I'd just like to thank you so much for a very cool and interesting talk. And we'll put your recording up on the YouTube channel, and those who want to follow up can take a look at it. So thanks again, Sebastian. It's really great.
Thanks again for your invitation and for all the questions.
Okay. Bye-bye.